Cascode current mirrors. In our discussion of current mirrors thus far, we have neglected channel length modulation. In practice, this effect results in significant error in copying currents, especially minimum length transistors are used so as to minimize the width and hence the output capacitance of the current source. For the simple mirror of figure B, we can write ID1 is equals to 1 by 2 mu n C naught x W by L 1 VGX minus VDH whole square into 1 plus lambda VDS1. As explained in chapter, the widths are actually scaled by placing multiple unit transistors in parallel rather than making a device wider. ID2 is equals to 1 by 2 nu n C naught x W by L to VGS minus VTH whole square 1 plus lambda VDS2, and hence ID2 by ID1 is equal to W by L2 by WL W by L1 into 1 plus lambda VDS2 by 1 plus lambda VDS1. VDS1 is equals to VGS1 is equals to VGS2 VDS2 may not equal VGS2 because of the circuitry fed by M2. For example, in figure, the potential at node P is determined by the input common mode level and the K source voltage of M1 and M2. It may not be equal to Vx. In order to suppress the effect of channel and modulation, a cascode current source can be fed as shown in figure A. If VB is chosen such that V gamma is equals to Vx, then Vout is closed when Vout closely tracks V reference. This is because, as described in conjunction with figure, the cascode device shields the bottom transistor from variations in Vp. With the aid of figure, the reader can prove that lambda Vy similar to delta Vy similar to delta Vp by GM3 plus GM3 plus GMB3 are now 3. Thus we say that Vy remains close to Vx and hence ID2 similar to ID1 with a high accuracy. Such accuracy is obtained at the cost of the voltage headroom consumed by M3. Note that while L1 must be equal to L2, the length of M3 need not be equal to L1 and L2. Here you can see the figure A, cascode current source. B, modification of mirror circuit to generate the cascode bias voltage. See, cascode mirror. How do we generate VB in figure? Since the objective is to ensure Vy equal to Vx, we must guarantee Vb equal to VGS3 is equal to Vx, or Vb is equal to VGS3 plus Vx. This suggests that if a 8 source voltage is added to Vx, the required value of Vb can be obtained depicted in figure B. The idea is to place another diode connected device M0 in series with M1, thereby generating a voltage Vx, thereby generating a voltage Vn. A voltage Vn is equal to VGS naught plus Vx. Connecting node N to the gate of M3 as shown in figure C, we have VG S naught plus Vx is equals to VGS3 plus Vy. Thus, if W by L3 by W by L naught is equal to W by L2 by W by L1, then VGS3 is equals to VGS naught and Vy is equals to and Vx equal to Vy. Note that this result holds. If M0 and M3 suffer from body effect. While operating as a current source with high input impedance and accurate value, the topology of figure C nonetheless consumes substantial voltage headroom. For simplicity, let us neglect the body effect and assume all of the transistors are identical. Then the minimum allowable voltage at node P is equal to Vn minus Vth is equals to Vgs naught plus Vgs1 minus Vth is equals to Vgs naught minus Vth plus Vgs1 minus Vth plus Vth. At is 2 overdrive voltages plus 1 threshold voltage. How does this value compare with that in figure A? If Vb could be chosen more arbitrarily as shown in figure, Vb could be so low that the minimum allowable voltage that P is merely 2 overdrive voltages. Thus, the cascode mirror of figure C weighs 1 threshold voltage in the headroom. Thus, is because VDS2 is equal to VGS2, whereas VDS2 could be as low as VGS2 minus VTH while maintaining M2 in saturation. Figure summarizes our discussion. In figure A, Vb is chosen to allow the lowest possible value of Vp, but the output current does not accurately track Iref because M1 and M2 sustain unequal drain source voltages. In figure B, higher accuracy is achieved, but minimum level at P is higher by one threshold voltage. A cascode current source with minimum headroom voltage. B, headroom consumed by a cascode mirror. Before resolving the issue, it is instructed to examine the large signal behavior of a cascode current source. In order to eliminate the headroom trade-off described above, we first study the modifications depicted in figure A. Note that this circuit is in fact a cascode topology with its output shortened to its input. How can we choose Vb so that both M1 and M2 are in saturation? We must have Vb minus Vth2 less than equal to Vx is equal to Vgs1 for M2 to be saturated, and Vgs1 minus Vth1 less than or equal to Va is equal to Vb minus Vgs2 for M1 to be saturated. Thus, Vgs2 plus Vgs1 minus Vth1 less than equal to Vb less than equal to Vgs1 plus Vth2. As a solution exists if Vgs2 plus Vgs1 minus Vth1 less than equal to Vgs1 plus Vth2, that is, if Vgs2 minus Vth2 less than equal to Vth1, we must therefore size M2 such that its overdrive voltage remains less than 1 threshold voltage. Now consider the circuit shown in figure B, where all of the transistors are in saturation and proper rationing ensures VGS2 is equal to VGS4 if VB is equal to VGS2 plus VGS1 minus VTH1 is equals to VGS4 plus VGS3 minus VTH3, and the cascode current source M3 minus M4 consumes minimum headroom. The overdrive of M3 plus that of M4 while M1 and M2 sustain equal. Drain source voltages allowing accurate copying of I reference. We call this a low voltage cascode. Here you can see in this figure. Modification of cascode mirror for low voltage operation. We must still generate VB for minimum voltage headroom consumption VA equal to VGS1 minus VTH1, and hence VB must be equal to or slightly greater than VGS2 plus VGS1 minus VTH1. Figure A depicts an example where M5 generates VGS5 similar to VGS2 and M6 together with RB produces VDS6 equal to VGS6 minus RBI1 similar to VGS1 minus VTH1. Some inaccuracy nevertheless arises because M5 does not suffer from body effect whereas M2 does. Also, the magnitude of RBI is not well controlled. Figure generation of gate voltage VB for cascode mirrors. An alternative circuit is shown in figure B where the diode connected transistor M7 has large W/L so that VGS7 similar to VTH7, that is VDS6 similar to VGS6 minus VTH7, and hence VB is equals to VGS5 plus VGS8 minus VTH7 while requiring no resistors. This circuit nonetheless suffers from similar errors due to body effect. Some margin therefore necessary to ensure M1 and M2 remain in saturation. Here you can see the circuit, low voltage cascode using a source follower level shifter. We should mention that low voltage cascodes can also be biased using source follower shown in figure. The idea is to shift the gate voltage of M3 down to respect to Vin by interposing a source follower. If MS is biased at a very low current density ID by W/L, then its gate source voltage is approximately equal to VTH3, that is Vn dash similar to Vn minus VTH3, and VB is equal to VGS1 plus VGS0 minus VTH3 minus VGS3 is equal to VGS1 minus VTH3, implying that M2 is at the edge of the triode region. In this topology, however, VDS2 is not equal to VDS1, introducing substantial mismatch. Also, if the body effect is considered for M0, MS and M3, it is difficult to guarantee that M2 operates in saturation. We should mention that in addition to reducing the symmetric mismatch due to channel length modulation, the cascode structure also provides a high output impedance. Thank you.